Section 2.6 is on rational functions. Okay, first they give you the definition of asymptotes in terms of limit notation. So the first one says x equals a is a vertical asymptote. So I'm going to go ahead and draw a random vertical asymptote. And I'm going to call this x equals a. Okay, I'm going to actually draw the horizontal one too so I can sketch the graph in. Okay, I'm going to call this y equals b. Normally rational functions that you have graphed look something like this, depending on the graph. Okay, so the first thing it tells you that if x equals a is a vertical asymptote, as x approaches a, and this little plus means from the positive side, f of x either goes to infinity or f of x goes to negative infinity. So this is x equals a. If I approach a from the positive side, that's from the right side, just to the right of this graph, or to this asymptote, the graph is increasing to infinity. So as x approaches a from the positive side, this graph, f of x, is approaching positive infinity. Okay, for the other side of the vertical asymptote, as x approaches a from the negative side, so just on the left side of a, if it's a vertical asymptote, the graph should either be approaching positive or negative infinity. So if I go to the left of a, okay, the graph on the left of a, x equals a, is actually f of x is approaching negative infinity. Okay, the definition of a horizontal asymptote, y equals b, is a horizontal asymptote. As x approaches infinity, f of x is either approaching b from the positive or negative side. Okay, so I'm going to look at this. As x approaches infinity is saying on the right side of the graph, y is getting close to y equals b. It's a little above y equals b, so I would say y is approaching b from the positive side. Okay, and then as x approaches negative infinity on the left side of the graph, way over here, y is also approaching b, and it's just a little lower than b, so y would be approaching b from the negative side. Okay, and I do know you have done these before. Okay, so we're going to graph f of x equals 1 plus 2x over x minus 1. Okay, I'm going to list the domain, I'm going to list the asymptotes, I'm going to find intercepts. Sometimes they ask you to find them, sometimes they don't, sometimes they're useful, sometimes they're not, and then I'm going to sketch the graph. Okay, since this is a rational function, there is a domain restriction. Okay, if I look at the denominator, it has x minus 1. I know that x minus 1 cannot equal to 0 because I can't have a 1 in the denominator, which means x cannot equal to 1. Okay, it didn't specify I need interval notation, so I'll leave it like that, although you're welcome to do interval notation if you would like. Okay, x cannot equal to 1, but at x equals 1, there is a vertical asymptote. Okay, on the graph, I'm going to go ahead and sketch my vertical asymptote. It should be a dashed line because it's not part of the graph, but it does help guide the graph. Okay, there's also a horizontal asymptote on this. I'm going to show you the way your book shows you to get the horizontal asymptote. In class, I will probably tell you the real reason this works. Okay, so they ask you to look at the leading term on the numerator and denominator. In this case, it's 2x over x. Okay, and then I'm going to think about that. If I had y equals 2x over x, the x's cancel, and I get y equals 2. So there's actually a horizontal asymptote at y equals 2. Okay, because it asked me to find the intercepts, I'm going to find the intercepts, and they might actually be really useful to graphing the graph. Okay, so x-intercept or y-intercept, doesn't matter which one you get first. And if it didn't ask me to find either, I might not find them unless they were really obvious. Okay, so if I want y, I plug in 0 for x, so 1 plus 0 over 0 minus 1, 1 over negative 1. Okay, so 0, negative 1 is a y-intercept. I'm going to go ahead and include that point. Okay, let's see, for the x-intercept, I set the equation equal to 0. So 1 plus 2x over x minus 1 equals 0. If I multiply the x minus 1 over, I get 1 plus 2x equals 0. Okay, so the x-intercept is at negative 1/2, comma 0. Okay, I'm going to go ahead and include that point. Okay, now for rational functions, if you have one good point on each side of the vertical asymptote, I'm fine with you sketching a graph from there. So I can already tell that this is going to get sketched over here. Okay, you had two good points on that side, so I'm fine with that. I just need you to have one good point on each side. Okay, now on the right side of the graph, I would like you to have one good point there. You don't need to show work for it, but when I glance at your graph, I should be able to tell that there is one good point. Okay, I'm gonna plug in a point. Okay, so to the right of the asymptote, x is 1, so I'm going to plug in 2. Okay, so if I plug in 2, and you wouldn't have to show work. If I plug in 2, what is that? 1 plus 2 times 2 over 2 minus 1. That's 5 over 1, so at 2, 5 is a point on the graph. Okay, I could have picked 3, 4, anything like that. I don't need your graph to be perfect, but again, I like to see one good point on each side. And if you have another way of figuring out the point, like using symmetry, that's fine with me. I'm just going to eyeball it and see that you have one good point and the rest of your graph is following the asymptotes in either direction. And your graph should look like it's approaching the horizontal asymptote as x approaches infinity and as x approaches negative infinity, and it should be approaching the vertical asymptote as well. Okay, we're going to graph another one. Okay, this is also a rational function. There will be a domain restriction. I'm going to go ahead and factor the denominator because that's going to make it more obvious what my domain restriction is. So that's going to be x minus 3 times x plus 2. Okay, because I can see I can cancel something, I'm going to cancel this out. And then I'll go back and think about what that means. Okay, in terms of domain, I want to make sure the denominator never equal to 0. So I'm going to go to this step here, and I can see x cannot equal to 3 and x cannot equal to negative 2. To 3 and x cannot equal to negative 2. You might be thinking, oh, but I crossed out the x minus 3. You did cross out the x minus 3, but if x could equal to 3, then you would have 0 divided by 0, which is indeterminate, and so it does need to be removed from the domain. Okay, it asks for a quote-unquote hole, which is also a removable discontinuity. If you cancel out a factor, you produce a removable discontinuity or a hole. Okay, because I canceled out x minus 3, there is a hole at x equals 3. Okay, x equals 3 is a line. Your hole is a point. So when it asks you for the hole, you need to write the ordered pair of the hole. So my hole is at 3, comma. To get the y value, I'm just going to plug it into my simplified function. So 1 over 3 plus 2 is 1/5. So at 3, comma 1/5, I'm going to have a hole. And again, that's an ordered pair because a hole is at a specific point location. Okay, for my asymptotes. Okay, now I canceled out x minus 3, so that does not produce an asymptote. It produced a hole. But I still have x plus 2 in the denominator, which means at x equals negative 2, there's a vertical asymptote. Okay, I also want to find the horizontal asymptote. Okay, I'm going to use the little trick your book shows you, but then it's going to be a little trickier because it's not going to work the same. Okay, your book likes to use the leading term on the numerator and denominator. You can do that either on the first step or the last step or any step in between, whichever one's convenient to you. You get the same result no matter what. Okay, I'm going to do it on the final step just because it's already simplified for me a little bit. Okay, if I only look at the leading term on the top, I get 1 over x. Okay, 1 over x makes no sense at all. So I'm going to go back to the definition of a horizontal asymptote. The horizontal asymptote occurs as x approaches infinity or negative infinity. Okay, so I'm going to plug in infinity, kind of, because you can't really plug in infinity. Okay, so if I have 1 divided by infinity, imagine you have $1, you divide it by every one of the billions of people in the world. If you have $1 divided by billions of people in the world, everyone essentially gets nothing. So 1 divided by infinity is about 0. So my horizontal asymptote is at 0. Okay, I'm going to go ahead and sketch that one. And I'm going to sketch the vertical one at negative 2. I am making them dashed because they're not actually part of the graph, but they do guide the direction of the graph. Let's see, I'm also going to graph the hole. At 3 1/5, there should be a hole. I'm just going to estimate I'm going to make it an open circle. Okay, because it asked me to find the intercepts, I am going to find the intercepts. I don't always find the intercepts if it doesn't ask me to, because sometimes I don't need them, and sometimes they're useful. Okay, let's see. For the y-intercept, I'm going to plug in 0. I'm going to plug it in the simplified expression because it's easier. 1 over 0 plus 2. Y-intercept should be an ordered pair. So 0, 1/2 is the y-intercept. Okay, and that's pretty nice actually. I'm going to go ahead and draw that half of the graph. Okay, I'm going to go ahead and get the x-intercepts and see if I can do anything with that. I'm going to try to use the final step. Let's see, if I do 0 equals 1 over x plus 2. If I times by x plus 2, I get 0 equals 1, which makes no sense. There are no x-intercepts, which makes sense because there's a horizontal asymptote going right through y equals 0. Okay, because I like you to have one good point on the left and right of your vertical asymptote, I would like to have one good point over here. You don't need to show your work for it. I just need to eyeball it and know that you have a good point there. I'm going to just plug in a number to the left. I'm going to plug in -3. You don't have to show work for it, but I just want to see that it's in a reasonably correct location. Okay, what was I plugging in? -3, so 1 over -3 plus 2 is 1 over -1. So that's -1. So at -3, -1 is a point in the graph. Okay, and with that 1 point, I'm going to go ahead and sketch the graph. It should go down towards the vertical asymptote, and then it should approach the horizontal asymptote as x goes to -infinity. Okay, now horizontal and vertical asymptotes you have done before. You may not have dealt with a slant asymptote before. Okay, so if the degree of the numerator is exactly 1 more than the degree of the denominator, then the graph is going to have a slant asymptote. I'm going to do a little sketch just to give you an idea of what that looks like. It would still have a vertical asymptote, but instead of a horizontal asymptote, it might have something like this. And then because the graph has to follow the asymptotes, it could potentially look like maybe like this, and then another one up here. It's still a function, it's just following a slanted asymptote as opposed to a horizontal asymptote. Okay, so why does this happen in the first place? Okay, let's look at this function here. Okay, for the vertical asymptote, I'm okay with that. I could find it really easily. It would be x equals 1. Now, if I tried to find the horizontal asymptote, I would look at the leading term on the top and bottom. So I would have y equals -3x squared over x. I would cancel an x out, and I would have y equals -3x. And then if I plugged in infinity into -3x, I would get -3 times infinity, which would tell me -3 times infinity is probably -3 infinity. I can't have a horizontal asymptote at y equals infinity. So it doesn't make sense. There is no horizontal asymptote. So there is a slant asymptote. Now to find the slant asymptote, you can either use long division or you can use synthetic division depending on the setup. Because the denominator on this is x minus 1, you could use synthetic division. If it were 3x minus 1, I would probably have to use long division. So I'm going to use long division just to practice it, but if you would like to use synthetic, you're welcome to do so. We should get the same result. Okay, so I'm going to divide numerator by denominator, so -3x squared. It's missing an x term, so I am going to put the 0x in its spot. And then I'm going to multiply this out. Let's see, that's going to be -3x plus 3x. Make sure you subtract when you go down. Cancel, cancel. Okay, so I get -3x plus 5. So that's going to be -3. -3x plus 3. I'm going to subtract down. Okay, and do make sure you go all the way till you finished your long division if you're doing long division. Okay, I'm going to write down what this would look like as a mixed number, and then I'm going to kind of adjust it because it's not actually accurate for the slant asymptote. Okay, if I wrote this as a mixed number, it would be y equals -3x minus 3 with a remainder of 2 over x minus 1. Okay, because I'm trying to determine where the slant asymptote is, I want to see what happens as x approaches infinity. If I plugged in infinity here, I would have 2 divided by infinity minus 1. Infinity minus 1 is still infinity. 2 divided by infinity essentially goes to 0. So this is irrelevant to what my graph is actually going to do. So my slant asymptote is going to be at y equals negative 3x minus 3. And I disregard the remainder because as x approaches positive or negative infinity, that remainder is going to go to 0 anyways. Okay, so the slant asymptote tells me which way my graph goes as it approaches positive and negative infinity. Okay, we're going to do one more example. We're going to find the asymptotes and we're going to sketch the graph for this one. Okay, it says find all asymptotes. I'm going to do the vertical asymptote first because it's easy. Okay, so if I want the vertical asymptote, if I look at the denominator, I can see x can't equal negative 1. Oh, yeah, because there's a vertical asymptote at x equals negative 1. Okay, now for this one here, because the degree of the numerator is higher than the denominator, this is going to have a slant asymptote. It's exactly 1 higher. If you forget that rule, that's okay. Just imagine you tried to find the horizontal here. I would do x squared over x. I would get x. When I plug in infinity, I get y equals infinity, which I cannot do. Okay, which means this has to have a slant asymptote. Okay, so let me do should I do long division? I'll do synthetic this time, just to show you the other way. Okay, if I'm doing synthetic, then I'm going to go ahead negative 1. Okay, I'm going to list the coefficients, 1, negative 2. Even though there's no constant, I have to put a 0 there, because this is x squared minus 2x plus 0. So just make sure you don't leave anything off on this. Okay, negative 1, negative 3, 3. Okay, and remember, I don't care about the remainder because as x approaches infinity, the remainder is irrelevant. Okay, so the slant asymptote is going to be at y equals x minus 3. Okay, and that's because this is 1x, this is a minus 3. Okay, I'm going to go ahead and graph the slant asymptote. Okay, it's a line. The y-intercept's negative 3. And from there I go up 1 over 1. Okay, I'm going to make it a dashed line because it's guiding the graph. Okay, let's see. Now I need a couple points to graph this. I need you to have at least one on the left and right side of the graph. It doesn't ask me to find the x-intercepts, but because it looks like I can do it really quick, I'm going to go ahead and find the x-intercepts to help me graph it. Maybe I might find the y-intercept if it was useful. Okay, so it's up to you how you want to do this. I can see that there is 0 and 2. So 0, 0, and 2, 0 are x-intercepts, which is also the y-intercept. Okay, that's enough to get the graph on that side. So I'm going to go ahead and sketch this. And then it kind of follows the slant asymptote as x approaches infinity. Okay, now I'm going to plug in one number on the left of the asymptote so I have an idea of where it's going to go. So I at least know if it's going to be up here or down here. Okay, so let me see. I'm going to plug in negative 2. Plug in negative 2, and it's okay if you can do it in your head, you just got to be careful. Negative 2 squared is 4, minus 2 times minus 2 is plus 4, and then negative 2 plus 1 is negative 1. So what is that, 8 over negative 1? So at negative 2, negative 8, I should have a point on the graph. 1, 2, 3, 4, 5. And when you get used to these, you might notice symmetry, features of symmetry that will help you match up the graph without actually having to graph it. Okay, that one dot tells me that the other half of the graph is going to be down here. Okay, and that's a pretty good sketch for this rational graph.